This is about 250 milliliters of tap water, and obviously it's not being stirred. And I believe for the stirring experiment I put in 3 drops of the dye. This particular dye is a gel dye. It's very viscous. It's used for like chefs for decorating cakes and the like. And so you can see, obviously, putting it in without stirring, you get some diffusion, but really the gel doesn't break up at all. This is a sample of tap water that had 3 drops of this gel food dye put into it. And what's different about the gel food dye than food coloring is that, well, that gel is very thick and it doesn't mix well with water. It's kind of, part of the whole function of it. So this has been sitting for about half an hour, and you can see obviously there's some blue in solution, but the vast majority of the dye is still accumulated at the bottom of the sample, the bottom of the beaker. It's not mixing. So just to kind of close this, so this is a stir that a student made. He put little feet on the end of it. And I'm actually not going to even suspend it, or I should say I'm not going to lower it. I'm going to get it centered. I'm not going to lower it all the way down into the beaker, and let's just see how well it functions. Obviously, if I lowered the stir, I could raise this, which would bring that in there. That would be the other way of doing it. That would make this go faster. Or if I sped it up, but within just 10 seconds, we've got adequate mixing. This is 100% raw honey. The ambient temperature is about 71 degrees Fahrenheit. Volume is about 200 milliliters. This is the stirrer at its maximum speed setting. If this was water, it would be out of control. But in this much more viscous liquid, it's straight as an arrow. So ironically, our setup is actually better for the more viscous materials than just pure water. Obviously, as the honey is stirred and warms up a little bit, it will change viscosity. But that'll be the next test where I cool it down to 0 degrees Celsius. The raw honey has been sitting in an ice water bath for 1 hour. And looking around the top of the sample, 8 degrees Celsius, plus or minus a little bit. Again, it's very cold. which is all we really need to increase its viscosity. So again, ice water bath for an hour. And I'm going to start off slow. You can see it's so viscous, it's actually moving the beaker a little bit. So I'm not going to try and turn up the speed anymore. Otherwise, I'd have to secure the beaker, because again, it is so viscous, it's got enough torque to actually move the beaker because it's not secured. However, it's doing its job, right? Stirring in an incredibly viscous solution. And again, you can see I'm trying to keep the laser in the honey itself, but of course it's translucent. So I could put a thermometer in there, but I just don't want to deal with cleaning it. However, ice bath for 1 full hour, and we are able to stir. I would not try and turn the speed up any further than it is right now, simply because it would cause the beaker to start to move. If we secured the beaker, then it'd be fine, but I do think this is right at the limitation of this particular piece of equipment, which is not in the least unexpected. So I've got just a little bit, like about a little bit over 200 milliliters of water in this beaker. The stirring rod is about an inch from the bottom of the beaker. I could lower it. This particular one was made by a student. It has little feet on it. And all I want to show is what happens if you start to throw stuff into the system. Make this go a little faster. That doesn't dissolve. In other words, obstructions. Now, obviously, you reach a certain point where you can't just keep throwing junk into the beaker. So these are rubber bands. And ironically, with this particular design, once it kind of does that, once it ties up with the stirring rod, it actually does help stabilize it a little bit, actually quite a bit. The point is, having material that is heterogeneous, just having different types of material in the solution that you're stirring, this particular design of overhead mechanical stir can compensate for that. Obviously, this has tremendous limitations as far as what you could use this particular mechanical stirrer for, but again, it works for what we do. And this is ridiculous as far as what I'm doing, throwing stuff in here. You would never want a student to do anything ridiculous like that. But again, it's to show worst case scenario if you had some material that isn't soluble, maybe a gel, for example, something like that, at least at first, that the stirrer can handle it.